Okay, first of all, thanks to the organizer for this opportunity. So today I will be discussing about how primordial gravitational background can act as a complementary probe of the dark matter annihilation. And this talk is based on this work. So the dark matter. So we all know that 26% of our universe is dominated by this kind of matter. Although there are several cosmological and astrophysical evidences there, but still now we are not very clear about this particle constituent. So to understand it, there are several phenomenological models over there, and out of them, weakly interacting massive particles are the most promising one. And on top of that, to satisfy the relic abundance for the present dark matter, the thermal cross section should have this specific value, and which is also a WIMP miracle. So till now, this WIMP scenario working very well and very smoothly until and unless it faces some challenges by the indirect detections, which put some stringent upper bound on the thermal cross section at the lower mass scale. So the question is, how can you revive from this situation, or these WIMPs, how can these WIMPs can satisfy the relic then? Now, this specific value of this thermal cross section is possible if we assume the dark matter freezes out during a radiation domination background. So, if anyhow the thermal histories get modified during the time of the freeze out, then this scenario may be resolved. So that is why in our work we have considered an early matter domination phase before the onset of the BBN, and we have assumed that this matter domination is occurred due to some domination of some long-lived massive particles. So obviously, this domination temperature and the decay temperature strongly depends upon the mass and the decay rate of these massive particles. So now, in presence of this early matter domination phase, the dark matter satisfies the relic if this quantity becomes unity. Okay. So this quantity, because here this decay temperature is related with the EMD parameter space, and this cross section and this freeze out temperature is related with the dark matter parameter space, which clearly relates between the relation between the EMD parameters and the dark matter parameter space. And this figure reflects the same. By tuning this EMD parameter, this whole parameter space can satisfy this relic. So the question is, how can we probe this whole phenomenological structure? So here the gravitational wave background comes into play. So the primordial gravitational wave background can probe this early universe cosmology, and from there we can extract out the information of the dark matter. And this builds the basic framework of our work. The dark matter parameter space can be directly probed by the indirect detections. On the other way around, this parameter space can be probed by the GW experiments, and hence there is a complementarity between these two types of experiments, GW experiments and the indirect detections. So in our work, we have considered these primordial gravitational waves generates during the quantum fluctuation at the time of inflation, and this is the gravitational wave spectrum. So at the left hand side represents the variation with respect to the EMD parameters, where the right hand side is the variation due to the dark matter parameter space. So now you can find the GW spectrum passes through a number of the GW spectrum passes through a number of GW detectors. So that is why we proceed to properly assess the detectional process, and that's why we have performed the signal to noise ratio analysis for the BBO, ET, LISA and the Mureris, and you can find this whole set of parameter region is greater than the signal to noise ratio is quite high. This is lies within the great we can detectability is quite high. At the same time, since this is the era of the precision cosmology, we also perform the Fisher forecast analysis to estimate the uncertainties on the dark matter parameter space while it is probed by the future GW detectors. Okay, so here at the end we have projected both the future reaches of the indirect detection searches and the GW detection searches, where you can find the overlapping region between these two type of experimental setups. Okay. Now, once we find this overlapping region, we further proceed to perform the Fisher forecast analysis. For an instance, in this region, ET can probe this this dark matter parameter space with the 1% uncertainty. So that's why this overlapping region reflects the complementarity between these two searches, between these two types of searches, gravitational wave and the indirect detection. So here here in this diagram we have described that the indirect detection is made by the gamma ray searches, and here we have made the same analysis for the neutron detectors. And at the end, I end up my slides by stating that the primordial gravitational background provides a novel opportunity to probe the dark matter, and also this links between the cosmological searches by considering the early universe cosmology with the traditional indirect searches. Thank you.
Thank you, Devaran. Quick questions? Maybe. Yes, please.
Can you go to the slide containing the spectral energy density of gravitational waves?
Yeah.
So what exactly is happening? Why is that rising there?
Oh, so yeah, in this figure we have considered a blue tilted spectrum. So
Primordial spectrum.
primordial spectrum is blue tilted. We also consider.
What
And
is the level of the tilt?
what is-
NT is
NT is
0.5.
0.5, both the diagrams.
Okay, because during the matter-dominated era, it will come down.
Yeah, so that is the come down, and also since there is some blue tilted spectrum, that's why it's now tilted over.
All right, thank you.